6-1, solving systems by graphing. So our objective for this section is to solve systems of equations by graphing and to analyze some special systems. Our essential understanding is that we can use systems of linear equations to model problems. Systems of equations can be solved in more than one way. One method is to graph each equation and find the intersection point. Okay, so the place where the two lines cross. Okay, so this chapter is mainly going to be about systems of equations and inequalities. Okay, and so we're going to look throughout this section on different methods of solving systems of equations. This first method, graphing, is okay. It works well if you have two equations in slope-intercept form that are easy to graph, numbers that are easy to work with, and if you wanted to model the system using a graph. Right? Using algebraic methods, which we'll see in the next couple sections, is usually a little more accurate and a little more reliable than this method. But we're going to start here. So first, linear equations form a systems of linear equations. So two or more linear equations are going to form a system. Any ordered pair that makes all of the equations in the system true is called a solution to the system of linear equations. And the solution to a system of linear equations is going to be the place where the two lines cross. And we'll see we'll see different ways that that's possible. Okay, so let's start with the simplest system. Okay? So what we want to do is we want to graph each line. And remember, to graph, we use my intercept point and my slope if it's in slope-intercept form, which it is. Okay? So my intercept is 2, so I'm going to put a dot at 2. And then my slope is 1, so I'm going to go up 1, right 1, up 1, right 1, up 1, or down 1, left 1, down 1, left 1. Okay? And that is enough to make a nice, mostly straight line. Do your best here. I think I curved a little bit at the end there. You want to do your best to make as straight a line as possible because that can affect the answer. So next, we're going to go down 2, and we're going to go up 3, right 1, up 3, right 1, and I'm going to get my line that looks something like that. And we can see that these two lines cross right there, which is point 2, 4. And if I wanted to, I can check my answer, and I should know, right, that's X, that's Y. I should know that if I plug this point into either one of these two equations, I'm going to make sure that they work. For instance, the first one would say that 4 is equal to 2 plus 2, which is true. So that works. Good. Or that 4 is equal to 3 times 2 minus 2, which is 6 minus 2 is 4. So that works as well. So this point works for both of these equations, which means it is a solution of the system. It solves both equations. Okay? With our got it problem, okay, we start at 4, and we go up 2, right 2, up 2, right 2, or down 2, let's say 2, up 2, right 1, down 2, left 1, down 2, left 1. Okay? And as I graph my line, try to make it as straight as possible, because if you don't, it could easily lead to a mistake. And then we start at 2, and my slope is 1, so that's up 1, right 1. I see it's diverging, it's going away, so I'm going to have to go back this way, and now I see a place where they had both cross. Okay, so I can continue this all the way down if I really wanted to. And my intersection point is right on the x-axis, which is point negative 2 comma 0. All right, and if I plug both of those in, you would see negative 4 plus 4 is 0, negative 2 plus 2 is 0. All right, so this point works, and it is the point where the two lines cross. Okay, now, doesn't always have to be so simple, right? We can also use this with a word problem to generate a system of equations. So scientists studied the weights of two alligators over a period of 12 months. The initial weight and growth rate of each alligator are shown below. So alligator 1, alligator 2. After how many months did the alligators weigh the same amount? Okay, so let's solve this by graphing. So in order to do that, I'm going to need to make two equations. So for alligator 1, we can say that its weight is going to be equal to 4 pounds plus a pound and a half per month. So that's 1.5 times the number of months plus 4. And for alligator 2, we have that the weight is going to be equal to 1 times t plus 6 pounds. Right? And so now I can take both of those equations and graph them. And for this particular graph, I didn't need any negative numbers because it wouldn't make sense to have a negative weight. Okay, so let's put time down there, and then weight on the left-hand side. And let's graph these. So I have slope-intercept already. Let's graph the first one. So at 4, that's my intercept. And I'm going to go up 1.5, right 1, up 1.5, right 1. So kind of a little bit harder to use this one because we have some fractions, but that's okay. We can figure it out. And we can get a nice approximation of my line. Okay. And then for the next one, which I didn't need this 1 here, right? It's just t plus 6. So we would go to 6. And now we go up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. And I can see that by drawing the points this way, it minimizes the chance of me making a mistake because I put a point right there for both sets of data. So my solution to this system is going to be 4, comma 10. 4 months, 10 pounds. After 4 months, both alligators are going to weigh 10 pounds. Okay? Let's look at our got it problem. Satellite radio service charges $10 per month plus an activation fee of 20 bucks. Second service charge $11 per month plus an activation fee of 15 bucks. What month was the cost of service the same? Well, let's just set this one up. So my equation is going to look like the cost is going to be $10 per month plus 20 bucks. And the cost for my other one is going to be $11 per month plus $15. Okay, so I can pretty easily, let's grab this graph. Whoops. I should have put a graph at the bottom. Let's copy this graph. Sorry about this. And we will paste it. And let's just graph these two lines really quick. So we would have not big enough. Okay, so let's make our own graph. Okay, so we have time and we have cost and we have one. Let's go 2, 4, 6, 8, 10, 12, 14 months. And my cost, let's go by tens. Go 10, 20, 30, 40, 50. Okay. So my starting point for the first one is 20, and we're going to go up 10, right 1, up 10, right 1, up 10, right 1, boom, boom. So there's my line, something like that. My scale is not super good, but it makes sense. All right, so the next one is going to start at 15, and we're going to go up 11, right 1, up 11, right 1, 11, right 1. You can see that it gets kind of messy to try to figure out exactly, especially with a graph that's not super accurate like this. It gets kind of hard to figure out where this crossing point is. And that is the biggest problem with solving a system by graphing, is unless your graph is perfectly scaled, and unless you make the lines perfectly straight, it's going to be hard to see where these lines cross. If I had made this nicely, they would have crossed at 5 months. But that's why some of the methods that we'll look at in the next section are much more accurate when we are trying to solve these systems. So, little vocabulary right here. So a system of equations that has at least one solution is consistent. A consistent system can either be independent or dependent. A consistent system that is independent has exactly one solution. For example, the problems that we just did in problem 1 and problem 2 are consistent independent systems. A consistent system that is dependent has infinitely many solutions. So if we are consistent, you're going to get an answer. We're going to get one answer for independent, infinite answers for dependent. And a system of equations that has no solutions is called inconsistent. So let's graph these and try to find the solution of each system. Now, first of all, the first equation is not in slope-intercept form. So the first thing I should do is make it into slope-intercept form. So let's add x to both sides, and we get 2y is equal to x plus 2, and divide everything by 2 to give me y is equal to 1/2 x plus 1. Well, notice that now both of my equations are the same. So if I'm going to graph them, I would start at 1, and I would go up 1, right 2, up 1, right 2, and I would just make my graph. And then when I made my other graph, it would be right on top of the other one. Okay? So if you have two lines that are right on top of each other, that is a dependent system, right? Because they intersect everywhere. And that's what it means when we say that they have infinitely many solutions. It means they intersect everywhere because they are the same line. Okay? Tough to tell that from the beginning, from the two equations before we changed the one to slope-intercept, but that's why we want to do that, for graphing and to compare them. Now for this one, they are in slope-intercept form already. Okay, the slopes are the same, but notice the intercepts are different. Okay, so the first one is graphs like this. Okay. And the second one, graphs like this. A little crooked, but you get the idea. In that, because the slopes are the same, they are never going to cross. And two lines that are never going to cross are called parallel. And the system is going to be inconsistent because they never cross. There is no solution. Okay. Let's look at two more of those. What is the graph of each solution, or of each system? Okay, so I'm not going to go through the whole graph here, but we see the slopes the same, different intercepts. So -3. So we got my first graph that's going to look something like that. And my second graph at 5, that's going to look something like that. They are never going to cross, so they are inconsistent. And for the second one, I have to divide everything by 3 first. And after I do that, I get y is equal to 3x minus 3. And I notice that I have the same line. So if I were to graph this, minus 3, 3x, up 3, right 1, up 3, right 1, I would graph the same line. Okay? So these two systems would be consistent, dependent. And if we get one answer, like this problem, then that's consistent, independent. Before graphing the equations, how can you determine whether a system of equations has exactly one solution, infinitely many solutions, or no solutions? The trick is to compare, put it into slope-intercept form, and to compare the slopes and the intercepts. Because we can see, let's take care of that. Sorry about that. We can see that these two slopes are the same, and they happen to have different intercepts. So they are parallel lines, which means that they are inconsistent. These two slopes happen to be the same, and they have the same intercept, which means that they are the same line, which means that they are consistent. Now, for our other solutions or other systems, the slopes were different. So if you have different slopes, the two lines are going to cross somewhere. So they are going to be independent. If you have the same line, same slope, same intercept, they're dependent. And same slope, different intercepts, parallel, and they would be inconsistent. So here's a little graph, or a little picture of all the stuff we talked about. One solution right there, where they cross. The lines have different slopes, and the equations are consistent and independent. These lines, purple, there's two on top of each other, the red and the blue. They're the same. Lines have the same slope, same y-intercept. They're consistent, dependent. Same slope, different intercept, one there, which means they are parallel and inconsistent. Okay? So I'm not going to go through all these. This will have one answer. Of course, this will have one answer, and I can solve that by drawing them and seeing where they cross. Both this will have one answer as well. And then before I graph this one, I should always turn it into slope-intercept form. So that would turn it to negative y is equal to negative 4x minus 1. So y is equal to 4x plus 1. Now I can graph this equation and see where they both cross. Okay. For the concert tickets, the cost is $10 each if you order them online, but you must pay a service charge of $8 per order, $12 if you buy them at the door at the night of the concert. Okay, so we have the cost is $10 per ticket, but you have to pay $8 per order, or the cost is $12 per ticket plus nothing. Okay, so we can see where these would cross. We can graph them and figure it out. Okay. Match each type of system with the number of solutions the system has. Inconsistent has no solutions. Consistent dependent has infinite solutions, and consistent independent has one solution. Suppose you graph a system of linear equations. If a point is on only one of the lines, is it a solution to the system? Well, let's think about this. Here's a line. Here's a line. That point right there, which is on one of the lines, is not a solution to the system. That is the solution, and it has to be on both. Can a system of two linear equations have exactly two solutions? Well, if you can think of a way to make two lines, which are straight, cross each other more than once, then you'd be smarter than all of us, okay? In order to make two things cross, right, it's got a curve. It's not a line anymore. Okay, there's no way to make a line cross more than two lines cross more than once. Suppose you find that two linear equations are true when x is equal to -2 and y is equal to 3. What can you conclude about the graphs of the equations? Uh, well, you can conclude that they have different slopes. You can also conclude that both are they both pass through this point, and that's pretty much it. Okay. So that was 6-1, solving systems by graphing.